What's up, guys? Josh Paul back here again with O-Chem Simplified, and today we're going to be covering acids and bases, and we're going to be looking at my preferred way of actually tackling acid and bases. Some professors like to use aereo, which really depends on the atom, resonance, induction, and a couple other factors. And it kind of complicates the whole process of learning acid and bases. So the method I'm going to teach you just is going to require a little bit of memorization. But once you have the memorization down, you're going to see that it's very easy to start tackling problems and understanding if you have multiple protons. How do you know which one you're going to attack if you have a base in solution? So without further ado, let's go ahead and dive right into what an acid is, and we'll then go into, conversely, what a base is. Alright guys, so you may remember from Gen Chem that there are three main definitions for acids and bases. The Arrhenius definition we're really not going to use because it's very general, and once you start getting into more complex reactions, you're going to need more specific definitions. So we're just going to start right off with the Bronsted-Lowry definition. So a Bronsted-Lowry acid is a proton donor, meaning that it has an available hydrogen to donate to another species, right? Remember, hydrogens are positively charged, right? So if an acid is a proton donor, then conversely, a base must be a proton acceptor and must be negatively charged, right? In order to accept a positive charge, you need to be negative, or you have to have some negative charge, right? So typically, we see the generic form of writing a Bronsted-Lowry acid as HA, and then the generic form of writing a Bronsted-Lowry base as B minus. So the definitions are very simple and very straightforward. An acid is simply a proton donor, so it will typically have an H in front of it or next to it that it can donate, and a base is just really anything with a negative charge that can accept a proton. Now here's an example of what I was just describing. So when we separate it out and actually show out the bond between the H and the A, we can see that the base is going to attack the proton, right? And when we attack that proton, when the B minus, right, when the arrow from the B minus goes to the H, what that means is that we're making a bond between the B and the H. And remember from Gen Chem, in order to make a bond, you must break a bond, which is why you have that second arrow below the bond, right, showing the flow of electrons back from the bond onto the acid, right? Allowing the acid to then gain an extra electron, right? Because remember, in that bond between the H and the A, there are two electrons, one electron from the hydrogen, one electron from the acid, right? So when the base forms a bond with the proton, right, then the bond between the H and the A has to break, in which case those electrons go onto the acid, making it A minus, right? And now when we have the reaction occurring afterwards, we produce a conjugate base and a conjugate acid, right? If you look at A minus resembles the generic form of a base that we talked about previously, right? Anything with a negative charge. Therefore, we call it the conjugate base because it came from the acid, right? And then the B minus, right, becomes HB. Remember, we said that an acid is a proton donor, which means there has to be an H available to be donated. So HB then becomes the conjugate acid from the base B minus. So that's the way that you should interpret acid-base reactions via the Bronsted-Lowry definition. Now, as stated before, I believe the best way to learn acid and bases is just to simply memorize the pKa's, right? There's about 15 to 20 of them, and it really does start to prep you up to the amount of memorizing you're actually going to be doing in organic, because there's no way to sugarcoat it. You are going to be memorizing a lot, right? And in this case, the memorization actually helps, right? There's no need to know aereo to figure out whether or not one molecule is more acidic than the other. If you know the pKa's, then right off the bat, you know which one is more acidic, and then you know which one is going to give up its proton if reacted with a base, right? So the way we interpret pKa's is The lower the pKa, the stronger the acid, right? What makes an acid strong means that uh, how you interpret that is that it's going to be more likely to give up its proton, right? So you're going to see a high H plus concentration when you're dealing with something that's a strong acid, right? So the lower the pKa, the stronger the acid, right? And just as we just discussed before, or I don't know if I mentioned it, but if I didn't, right, the stronger the acid, the weaker the base. So this is a concept that you're really going to have to hone down on because it's going to really help you see the connection between memorizing your pKa's and the relationship between acids and bases. So real quick, we'll just touch up on what a Lewis acid is. Really, you don't have to worry about this until you start to reach nucleophilic substitution reactions and elimination reactions and so on and so forth. But a Lewis acid is, you can think of it as the complete opposite of a Bronsted-Lowry acid, right? What is the opposite of a proton, right? A Bronsted-Lowry acid is a proton donor. The opposite of proton is an electron. The opposite of a donor is an acceptor. So a Bronsted-Lowry acid is a proton donor, whereas a Lewis acid is a electron acceptor, right? And conversely, a Lewis base is an electron donor, right? An example of this can be seen below with the fluorine, right? The fluorine has that minus charge, right? Because it has a full octet, right? Therefore, fluorine has electrons that it can donate. Therefore, the fluorine, the F minus, is going to be the Lewis base, right? And the BF3 is going to be, right? We see that the BF3 is accepting those electrons and forming a bond with the F minus. Therefore, it is the Lewis acid because it is accepting the electron pair in order to form a bond. So that's how you interpret a Lewis acid versus a Lewis base. Like I said, you don't really have to know too much about this until you really hit different types of molecular reactions. So again, why not learn aereo? Aereo really, you start off with the atom, and then from the atom you determine whether or not, depending on size and polarity, that's going to influence it. Then resonance is also going to influence. Then induction is going to influence, and then orbitals. So you can see that there's a lot of different things that you have to, I guess we could say, assume, right? Now, why am I using the word assume? Remember the quote from the beginning of the video. So let's go back and take a look at that quote. When presented with competing hypotheses to solve a problem, one should pick the solution with few assumptions, right? What does that mean, right? When you're looking at aerial, you're making a lot of assumptions based on the atom, the resonance, the induction, and the orbital, right? Now, when you have the pKs memorized, there are no assumptions. Therefore, when you're competing between hypotheses of which is the correct answer, you already know it right off the bat. So you're eliminating any human error. You're eliminating any chances of similarities between atoms and resonance that may confuse you, right? When you have that set integer value known, then you can compare directly whether or not one molecule is more acidic than the other, right? Or whether, I should say, whether or not the proton from the species is more acidic than the other. So that's my justification for why aereo is just probably not the best method to learning acid bases and why you should just put in the extra time to learn the pKa's. All right, so once again, just a quick recap. The stronger the acid, the weaker its conjugate base, right? And a low pKa means a strong acid, which means a weak base. And a high pKa means a weak acid and a strong base. So this relationship is going to be very important because if you know the pKa of a proton for a specific species, then you can completely compare whether or not you're going to have a stronger or weaker acid. And then if they're asking you about basicity, then you can just flip whatever results you get because acids and bases are almost completely opposite in behavior. So guys, to simply put it, there's no other way around it. you have to memorize your PKAs. So go ahead, pause this video or let it play out while you write it out. There's going to be some classical music in the background to help you concentrate. As you memorize these PKAs, I suggest using flashcards. If you want to use, I would use handwritten flashcards instead of Quizlet or any other type of app, just so you can visualize the function of groups. But like I said, no other way around it. Let's memorize these PKAs, because once we start doing practice problems, you're going to see why the PKAs are so crucial.